All right, in today's lesson, we are going to go over lesson 4 of chapter 8, which is all about heat and energy. Today, specifically, we're going to go over thermal energy, heat, and then temperature as a whole, which we'll review first. We last left off with lesson 3. We were talking about energy. Still, we were talking about just mainly kinetic potential, and then we got into the law of conservation of energy, which, if you don't remember, means that energy cannot be created or destroyed. It just gets converted from one type to another. We're going to build upon that. I put a picture of a pie here, not to make you hungry, but if you have pie, you can eat it while you're watching this, of course. But we're going to get back into pie later on. So just kind of keep that back in your head a little bit, and we'll use it for a couple of examples. Okay, so what is the difference, what determines the temperature of an object? So temperature is a measure of how hot or cold something is compared to a reference point. And I put a picture of the thermometer here. We all know what a thermometer looks like in our own mind, because now there's just so many different types of thermometers. We have digital thermometers, we have mercury thermometers, we have replica mercury thermometers, which you most likely would think of when you see a picture like this. But whatever it is, a thermometer is measuring how hot or cold something is compared to some reference point. Okay. Now let's talk about how these thermometers work. Okay, these type of thermometers, the one that's shown on which you're seeing the picture, has a liquid in it. And as that liquid heats up, it's actually expanding and it's taking up more space. So because it's in a tight tube, it rises from its reservoir and shoots up. And wherever it ends up, that's the temperature. Okay, so just so you know how they work. Okay, so what determines the temperature of an object continued? So temperature is a measure of kinetic energy of the particles in an object. Okay, so let's talk about what that means. Okay, an object heats up its particles, and when that happens, when an object's particles heat up, they move faster and faster. As you can see in the pictures below, we have temperatures of different at different levels. For example, one temperature is 5 degrees. The second picture, it's 20 degrees. The third picture, it's about 40 degrees. It's all in measuring the temperature of a liquid. As you can see in the first picture, the particles are held a little bit tightly compacted. They're a little bit further out in this one. There's a little bit further out in the third one. Okay, so not much difference in the picture necessarily. Okay, but what is happening is as they move further and further out, it is heating up, which is a review of things we learned in 5th grade and things we went over before we are having school at home. We talked about this. So as the particles expand their reach, as they go back and forth, just a little bit more of the kinetic energy, it causes the temperature to rise. So again, just a review. Temperatures, they measure the average kinetic energy of the particles in an object. As an object heats up, its particles move faster and faster. And you can go online and actually see images like this, and you can actually see the particles moving. Okay, but before we get into that, I want to talk to you a little bit about temperature scales. Okay, but before we do that, I'm going to actually show you a video about particle movement.
All right, guys, what we're looking at here is a simulator that shows us what the particle motion would look like in a cold liquid and in a hot liquid. So here at the cold liquid, we can see that the particles are pretty close together. They're in motion. They're kind of moving and sliding past one another. But they're not moving as quickly as a gas, and they're also not in a fixed shape like a solid would be. So we can move the slider and observe how that will change the motion of the particles. So as we heat this up, we see the molecules start to move faster and they're kind of bumping into each other, but also we can see how the spaces between them are larger. So here in that hot liquid, we can see how as we've increased the temperature or heated the substance, we see an increase in the speed of the particles. And we can see an increase in the spaces between the particles. Now, if we cool this liquid down, we see a decrease in the speed of the particles, and we see a decrease in the space between them. So this helps to show us what the particle motion looks like in a cold liquid and in a hot liquid.
Okay, so getting back to and building upon what that video was just showing, the more you heat up a liquid or anything, the faster you're going to move those particles. And in doing so, we're creating more of something. We're going to talk about what that something is in a second, but we should stop right here and talk about temperature scales, because there's different temperature scales. We use different ones depending on what exactly we're doing and depending on what we're doing it for as well. So let's talk about the most common one, the Fahrenheit scale. So the United States uses the Fahrenheit scale to measure temperature, okay? And on the screen, you can see they have the Fahrenheit scale. Okay, very simple scale. We teach you it probably as early as we can. Yeah, I'm sure in pre-K 3 they started talking about temperature scales to you, the Fahrenheit scale at least. But most countries actually use the second one, the Celsius scale. And there are equations you could use to convert Fahrenheit to Celsius. But it's simpler to estimate using a thermometer like the ones that you see all the time. Temperatures that line up like 32 degrees Fahrenheit and 0 degrees Celsius are equivalent. Many scientists actually use this third one. Third one's called the Kelvin scale. Celsius and Fahrenheit scales are divided into degrees, but the Kelvin scale actually isn't. Kelvin scale uses not a degree sign to show it, but just the K for Kelvin. A temperature change of 1 Kelvin, is the same temperature change as 1 degree Celsius. 0 degrees Kelvin, or what we call absolute zero, is the lowest possible temperature. At absolute zero, particles have no kinetic energy. 0 K is equivalent, or should be equal to, negative 270 degrees Celsius. So let's look at that here. So when we talk about the Celsius scale is helpful in many aspects of life, in a light scientific way, and then just normal everyday way. So let's talk about the Celsius scale first. Celsius scale is essentially based off of water. What's the freezing point of water? What's the boiling point of water? So freezing point of water, they found out what that was. They said, okay, that's going to be 0 degrees Celsius. They started boiling water. They measured that with the same type of thermometer and said, this is going to be 100 degrees Celsius. So that's what we have with the Celsius scale. Fahrenheit, it's an older type, 32 degrees for freezing of water, boiling point of water, 212 degrees Fahrenheit. So it wasn't based off of water at all. This is a scale with a good amount of range. Now the Kelvin scale, we needed something. Scientists wanted something to measure absolute zero, okay, which is almost impossible to achieve in any aspect of life, whether in nature or in a laboratory. It's extremely hard, essentially theoretical, to achieve absolute zero, to have no kinetic energy. Okay, but we still, as scientists, wanted a way or a scale to measure this. So that's why, and partially, Mr. Kelvin came up with his scale. Okay, as you can see on the screen, I also gave you just another type of chart used when talking about these three different scales to kind of show you the comparison in the numbers. So, for example, boiling point, 212 Fahrenheit, 100 degrees Celsius, 373 Kelvin. Don't worry about what it says at sea level. That doesn't concern us just yet. Average room temperature, so you know, 68 degrees Fahrenheit, 20 degrees Celsius, 293 Kelvin. So which one would you really use in everyday life, Fahrenheit or Celsius? Okay, which one would you want to use as a scientist? What gives you the best range? Kelvin. Now let's move on to what this lesson's really about: thermal energy, heat. And then how are they the same, how are they different, common misconceptions. So temperature, thermal energy, and heat are closely related, but they are not the same thing. They're just closely related, not the same thing. They may have some similar look to them when you think about those three words, but really by definition, they are different. Temperature is a measure of the average kinetic energy of the particles, the individual particles, in an object. However, it is not a measure of the total amount of energy in an object. So I'm going to repeat that. Temperature is a measure of the average kinetic energy of the individual particles in an object, but it is not a measure of the total amount of energy in an object. Thermal energy is the total energy of all the particles in an object. It depends on the temperature of the object. It depends on the temperature of an object, the number of particles in it, and how those particles are arranged. Now, I said earlier we're going to talk about a pie. Okay? If you have your book by you, turn to page 302, and you can actually see this picture that I took a picture of and put on the PowerPoint. So we have pictures on here, 2 sets, 4 pictures of a pie. Both pies in the first picture are intact. In the second picture, it seems like I got to one of them and ate some of it. Seems about right. What pie? Apple pie. But if you notice, they have some degrees on these. The total amount of thermal energy an object has depends on its temperature and how many particles it contains. So while the picture with 100 degrees Celsius and a 200 degrees Celsius, while they are different temperatures, they have the same amount of particles. So what does that mean? It means they both have the same amount of thermal energy, right? Maybe. Yeah, think about it. If these 2 pies have the same temperature, but we're missing a quarter because Mr. Vitale went and got a Mr. Vitale slice of it, fourth of the pie is missing. So does it have the same amount of thermal energy and particles? I want you to pause. You're eventually going to do this anyway, so it allows you to do it right now. Pause, get your book, and actually work on this apply a question on 302. And then when you're finished, when you think you're finished, come back to it and we'll discuss it. Okay, so now that you've completed it, you can see that they're actually not apple pies like my favorite pies. They're chicken pot pies, but I like to think whenever I see pie that it's apple pie. So in the top 2 panels, you had to circle the pot pie that contains more thermal energy. Okay, so out of these 2 panels, which one did you circle? Okay, so in the first panel, out of the 2 chicken pot pies that are totally whole, one's 100 degrees Celsius, one's 200 degrees Celsius. Which one would you have circled that has more thermal energy? Okay, this one, 200 degrees Celsius, has more thermal energy. Now let's figure out why. Well, they're both whole, so they both have the same amount of particles. And thermal energy is the total energy of all the particles. So by definition, if they both have the same amount of particles, then the one with most thermal energy is the one that's warmer. So the one with 200 degrees is warmer. Let's look at the next picture. They're both the same in terms of temperature this time, but what's missing? Well, a quarter of the pie is missing one of them. So which one has more thermal energy? If you circled the one on the right, you are correct. Why? Simple. It has more particles than the one on the left. Okay, since this one is missing this part, it has less particles by definition. Now, So let's say this was filled in. If I didn't get to it, okay? If I didn't get to this at all, go ahead and clear this out. If I didn't get to this pie at all, Mr. Vitale didn't take his Mr. Vitale cut of it. Okay, which one would you have circled? Well, you would have circled both because they would have been equal. Okay, but since it's missing part of it, you would have circled the one on the right. All right, hopefully you got that correct. All right, moving on. So what is thermal energy continuum? Well, heat is something entirely different yet related. Like I said before, heat is the transfer of thermal energy from a warmer object to a cooler object. Think about it anytime you put your hand on a desk. Okay? And you may have did this depending on which class you're in. You may have did this with me already. Put your hand on a desk and you keep it there for a couple of minutes. Okay, at first it's going to feel cool, most likely to you. When you pick it up and put it back there, it's going to feel warm. Why? Well, you transfer some of your heat to the cooler object. So heat is the transfer of thermal energy from a warmer object, in this case you, to the cooler object, your desk. If you're not good with that example, let's think of one from your memory bank. Okay, think about the last time you're in church. Okay, you're sitting there a while. We get the communion. You go receive the Eucharist. You come back. And when you first sit in the pew to put the kneeler back down, you can literally feel where you were sitting before. You could literally feel if you're sitting just out of place. Why? Because part of where you're sitting feels cooler and part of it feels warmer. Why? You transferred some of your heat to the pew. The warmer object will eventually cool down, or does cool down, and the cooler object will warm up until they are the same temperature. Okay, so the pew, the desk, it was warming up, and you were also cooling down. Okay, until y'all become equal. Heat is measured in units of energy, actually. And if you don't remember what the energy units are, they're called joules, Joules. And we use a J to represent it, okay, because we can't have naked numbers in science. In the next chapter, we're going to go more into energy, but we did introduce it already to you before we went virtual. So heat is measured in units of energy. We call those joules. That's it for lesson 4. Please stay tuned for lesson 5. Keep up the work that you're doing. A lot of y'all are doing things right on time. Some of y'all are getting things in early. That's fine as well. I'm going to continue putting things up about a week in advance. Thank you and stay good.